Welcome to lecture 3. So, in this lecture, we will talk about modeling timing constraints in real time systems. So, this will be an extension of what you have studied with finite state machines, FSMs. So, real time systems are, fundamentally different from traditional systems. Tasks have deadlines associated with them in the sense tasks have to complete within a certain period of time. So, this is something that you want tasks to do to complete within a certain period. They are classified based on the consequences of a failure. So that is why we have three kinds of real time systems: hard, soft, and firm real time systems. So I will discuss them in some detail. So, first, hard real time systems. So, if a deadline is not met, the system is said to have failed. So, this is a standard definition of real time systems that we have been looking at for the last two lectures, that tasks have to finish within a certain deadline. Otherwise, they are said to have failed. And the task deadlines can be of the order of microseconds, milliseconds, even seconds. So many of the hard real time systems are safety critical. And examples, of course, prime examples are aircrafts, but also industrial control applications, onboard computers of aircraft, defense equipment, missiles, robots. So in this case, tasks have to complete. In firm real time systems, it is all right if a deadline is missed occasionally. The system does not fail. So, this is far more tolerant of missed deadlines. The results produced by a task after the deadline are rejected, but the system on a whole does not fail. See, if this is my graph where the time is the x axis and the utility is on the y axis, of course, the utility of a result becomes zero after the deadline has passed, but the task per se does not fail. What would be an example? A video conferencing application. So assume that I'm doing video conferencing. So I expect 30 frames per second, so one frame every 33 milliseconds. But if a frame arrives late, I just drop it, right? So it may cause a little bit of jitter, may not. It depends upon the type of application. But that said and done, I just drop the frame and I just go ahead. Anything with telemetry, vision, whether measuring something, surveillance, satellite based surveillance, occasional jitter, I'm okay with it. I'm fine. Soft real time systems, if a deadline is missed, the system does not fail. So, this is the most tolerant category of real time systems. Where, let's say, we miss a deadline for whatever reason, the system does not fail. So, the utility curve, well, the utility is maximum until the deadline. So, the deadline point is this. But after that, instead of it becoming zero like in a firm real time system, it gradually kind of declines to zero, gradually. So the performance of the system degrades, but the utility of the result decreases, needless to say, after the deadline. But the system per se does not fail. So another definition could be with probabilistic requirements on the deadline. You can say that 99% of the deadline should be met. So this is something that you can say. You can specify, for example, for instance, that 99% of the deadlines need to be met. I'm okay with 1% of the tasks not meeting the deadlines. Or you can further look at this period post the deadline and then say that, look, maybe out of that 1%, 10% need to be here, 10% over here, and so on. So, examples of such soft real time systems, for example, would be a railway reservation system where we need to, or an airline ticket system where we need to make a reservation, we need to do a booking. If we expect the response to come within 10 seconds, it takes 30 seconds, that's fine. It will cause some degree of hardship to the passengers. But that said and done, it's okay, it's not that bad. And the same is with web browsing. If, let's say, a site does not come back immediately, but it takes 2 minutes, well, that's fine. You don't like it, but nothing catastrophic is going to happen. So, in fact, for all interactive applications, a little bit of delay, a little bit of jitter is not going to kill you. right? So now coming to the types of real-time tasks, so we have discussed this once in chapter 1. We'll have periodic, sporadic, and aperiodic tasks. So periodic is when tasks repeat after a certain fixed interval, which in most sensor-based cases, this is indeed the case, that there is a period. So once in every period, the tasks repeat. So we have a period here. This is indeed the case that these tasks keep repeating. Sporadic is when the tasks recur at random instance. But of course, we do specify some constraints. It's not a constraint-less system that between, let's say, two of these tasks, T1 and T2, there is a delay and there is a bound on it, right? So there is a minimum, there's a bound on it that, it needs to be more than something, greater than something. So aperiodic is same as sporadic, but it is just that the minimum separation can be zero. In the sense, this is truly there are a constraint-less environment for events. So now we will define timing constraints, which is the mainstay of this chapter. So timing constraints are typically defined with respect to some event, and an event can occur in general at any instant of time. But an event can also have a duration. In the sense, you can say that the event can also occur over a duration, but the duration can be, let's say, 2 milliseconds. So the event would be occurring for 2 milliseconds. It can be generated either by the system or its environment, which is, which is encompassing what we have discussed earlier. Generated by the system would be an event. Generated by the environment would be an event, and generated by the system would be a response. But let us say, for the sake of, for the scope of this lecture, we'll call both an event. So events can then be classified into stimulus events and response events, right? Instead of event and a response, the terminology that we will use in this lecture will be a stimulus event and a response event, right? Stimulus is provided to the system, and what you get out of the system is a response. So stimulus event is generated by the environment. You capture it via sensors. It could be asynchronous and aperiodic in nature, could also be periodic. For example, a user pressing a button on a telephone set, right? This is not something that can be predicted, right? This is aperiodic. And so this event would act on the telephone system, and we expect some output. A periodic stimulus event will be the periodic sensing of temperature in a chemical plant. So this would be a periodic event, because every p milliseconds or p microseconds we'll be getting the temperature. A response event, on the other hand, is produced by the system. Typically, in response to some stimulus events, you produce a response. So in comes a stimulus, out goes a response. For example, it could be that in a chemical plant, as soon as the temperature exceeds 100 degrees C, then we respond either by switching off the heater or switching on the heater or something of that nature. So now comes the classification of timing constraints. So the timing constraints can be classified like this, such that we can quickly identify these from a problem description. So we can have either performance constraints broadly or behavioral constraints, right? So these are different kind of constraints. So let's look at them. So performance constraints are typically imposed on the response of a system, because as far as we are concerned, if an outsider is looking at a system, the outsider will look at the responses. And the responses are the true outputs. So the responses of a system are the true outputs of the system. So then the outsider will look at them, and then basically, based on their behavior, the constraint would carry that. And the behavioral constraints would be those that are imposed on the stimuli generated by the environment. So basically, it's the input side. So this is like the input side. This is the output side. So both performance and behavioral constraints can be classified into three types. So basically, regardless of whatever is the constraint on the stimulus or on the response, this would be the classification. Delay constraints, deadline constraints, and duration constraints. Okay, the three Ds. So that is the most important. What we need to remember here are the three Ds: delay, deadline, and duration. So the delay constraint expresses a minimum time delay in the sense it says that, look, let's take two events and let those events be called E1 and E2. Let the function T E1 give the time of the occurrence of event E1. So this needs to be greater than equal to D. So this is typically what we were using in defining a sporadic event where D is non-zero, right? And TE2 minus TE1 is greater than equal to D, which means that E2 has to occur at least D units of time after E1. That is a delay constraint, and this is between two arbitrary events. If E2 occurs before the delay, then of course the system is an error. The other is a deadline constraint, which is the reverse of the delay constraint. It expresses the maximum possible separation between two events. Between any two arbitrary events, E1 and E2, it says TE2 minus T1, E1 has to be less than equal to D, where if let's say one event is the start of processing, the other is the end of processing, for example, or you whatever, just two events, or one event could be the sensor receiving something and the other would be the deadline elapsing, and then this one is E1 and this is E2, then clearly TE2 minus TE1 is less than equal to D. Sorry, I stand corrected. Let me redefine them. E1 could be the event that indicates that we have read something from the sensor but not processed it. And E2 could be the time at which we finish processing. All right. So what we want is TE2 minus TE1 to be less than equal to the deadline, which means we are finishing the processing within D time units of receiving the data. Right. So deadline and delay are the opposite of each other. Delay is required for sporadic tasks, right, to specify a minimum separation, and the deadline enforces a maximum separation. The duration constraint is different. So basically, this is for an event which is not a point event, but which acts over a period of time. So then we can say that, look, this is the duration, right? And the duration can be expressed as a minimum type or a maximum type, in the sense you can say that the time for which the event acts, maybe the minimum time is X or the maximum time is X. Now, coming to the minimum, once a duration event starts, it must not end before a certain maximum time. That is the, sorry, it must not end before a certain minimum time. So, this basically says that, look, once an event starts over here, the time for which the event acts, okay, so every event now is not a point thing, it is more like a time range kind of phenomenon. And in this case, so basically you can say that the moment I click the save button, for instance, then the uh, let's say your word processor freezes because then it saves the document. So this could be the moment of my clicking it, and this could be the moment of the document unfreezing. So there could be a minimum constraint on this, or there also could be a maximum constraint on this, right? So this could be that a duration event starts, it must end before a certain maximum time, which means that the E1 event is actually working over this entire period. And this period or this duration can also be specified with a constraint. So typically we use the delay and deadline constraints. We don't use the duration constraint that frequently. But that said and done, this is definitely a member of the 3Ds club. And particularly when an event is not a single point, but essentially the time range between 2 points, the duration constraint is very useful. So let us now provide examples of looking at these timing constraints in the context of an example system, which is a traditional telephone network. Okay, so this is a very simple example which all of us can understand. So a deadline can be defined between two stimuli, which is a behavioral constraint, which basically means that this is being imposed on the stimulus. So what you can say is once a user completes dialing a digit, the user must dial the next digit within the next 5 seconds. So this is typically the case in a phone line, right? That once I dial a digit, if I don't dial the next digit within the next case seconds, then the call kind of auto terminates. So in this case, I say that I must dial the next digit within 5 seconds. Otherwise, an idle tone is produced in the sense my calling operation terminates. This is a stimulus to stimulus deadline. So my clicking the button is a stimulus, the first button click, and the second button click is one more stimulus, is a stimulus to stimulus deadline. I can have a response to stimulus deadline, where a deadline is defined on the stimulus from the respective response event. This is again a behavioral constraint which is imposed on the stimulus. So let's say once the dial tone appears, right? So the dial tone appearing is the start point. The first digit must be dialed within 30 seconds, right? So this is, of course, a constraint on what what I do. So typically, when I pick up the receiver of a telephone, then the dial tone may take some time to appear. But once it appears, and let's say if I don't dial, it basically means I don't want to make a call. So in that case, at least the way it used to be in olden days, the dial tone would go away. Or let's say the phone would somehow decide that I'm not interested in making a call. So the time that maybe that could be given to me is 30 seconds within which I need to click a button. So this is a response to stimulus kind of deadline setting. If I don't do that, the system will enter an idle state and then I may have a separate tone in the phone to indicate the fact that I'm idling. So let us now look at a performance constraint, which is a response to response deadline example, where the deadline is being defined from one response to another. So needless to say, this is the performance constraint. So basically, the start event is that a ringtone is given to the callee. After that, the ring back tone, so which basically means that I am dialing, A is dialing B. So in this case, A is the caller and B is the callee. So once the call is connected, B is going to get the phone at B's end is going to start ringing. So this is what is being meant by saying that the ring tone is being given to the callee. So the phone at B is going to start to ring. So the ring back tone, so A also needs to hear that ringing, right? So in the sense, the moment a phone connects, I hear the ringtone. So this ringtone at A, at the caller, must be given to the caller within 2 seconds. In the sense, it rings first at the callee. But within 2 seconds, which is a deadline, the caller also needs to get the call, also needs to get the ringtone. So this is an example of an RR deadline kind of setting with our phones. Otherwise, of course, if this doesn't happen, the call gets terminated. All right, so this was a performance constraint as we saw. And now we go to a stimulus to response deadline example. So here the deadline is defined on the response from the respective stimulus. This is again a performance constraint because primarily it is being imposed on the response. So let's say the receiver of the handset is lifted. The dial tone must be produced by the system within 2 seconds. So this is the stimulus over here. This is the response. So we from the stimulus, we go to the response. So this is an SR deadline constraint. And the deadline in this case is 2 seconds. So otherwise, if this doesn't happen, so which means that if the dial tone is not produced This basically means that the phone is not being able to connect to the nearest PSTN box. So this basically means that a beeping sound is produced until you replace the handset and try to pick it up once again, right? So this is for a fixed landline phone, and so pretty much mobile phones also do something similar in the dialing process, but we don't get to see that. But in a landline phone, we see the dial tone. So we actually we see the steps, we hear the steps. So then we can have an SS type delay constraint. Again, this is a behavioral constraint because an S is involved over here. So once a digit is dialed, the next digit should be dialed after at least 1 second. So as you can see, this is not a delay, this is not a deadline constraint, it's a delay constraint. So this is basically saying that we are not supposed to kind of press two digits at the same time or in quick succession. This is not something that we are supposed to do. What we are supposed to do is we are supposed to press one digit and then press one more digit, but there has to be a minimum separation of 1 second. Hence, this is a delay constraint. If this doesn't happen, then of course this will lead to an error. So this will produce a beeping sound until the initiator of the call replaces the handset. So now let's come to a duration constraint. So duration constraint, as we have described earlier, specifies the time interval over which an event acts. So if you press the button of the handset for less than 15 seconds, for instance, it will connect to the local operator. So basically, if we go to hotels and so on, we always have the option of talking to the reception or the operator, right? For something. So it always has a room service button. So if I press that for less than 15 seconds, it will connect me to room service in a hotel. If I press it between 15 and 30 seconds, it will connect me to one more kind of operator, let's say to make an international call. And I press it for more than 30 seconds. Then on releasing it, it will produce the dial tone. So as you can see, based on the duration, different actions are taken. So of course, in this case, 0, 15, and 30 are only for the purposes of an example. In practice, we'll not press a button for that long, or at least I hope not. But what it is trying to say is that it is trying to capture the duration of the press. So for example, when I click the power button on my laptop, well, if I just click it once, then the system, uh, nothing much will happen. I don't want to click it right now because I'm recording the video. But definitely, if I click it for more than a certain duration, the system will get powered off, right? But if I click it just once, so at least in my previous laptop, the screen used to refresh. So basically, the duration determines a lot. And this is the third D of the three Ds constraint. So what have we discussed? We have discussed different timing constraints, performance constraints, and behavioral constraints. Performance constraints were on the response. So that is why you see response coming at the end. And then there were, of course, the three Ds are over here, delay, deadline, and duration. And then for each one of them, we could have RR, SR, RR, and SR, which are basically the delay and deadline constraints so basically they come whenever a response is there. Similarly, behavioral constraints can be broken into delay, deadline, and duration. So in this case, the stimulus comes at the end, which basically is so behavioral constraint imposes a restriction on the stimulus. That is why it is there. So now that we have taken a look at these constraints, let's see how to exactly model them. So first is why model timing constraints? Well, the key idea is it helps us to formally specify a system. The moment we have formally specified something, we can understand and analyze it. We can automatically generate code for it. And it will help us, get a deeper insight into real-time behavior. So several approaches can be used. So one specific approach, which is very popular, which goes back to 1985, proposed by Dasarathi. It is basically like this, that a state in an FSM is defined in terms of the values that are assumed by an attribute, for example, the values of the entire system. The states of an elevator can be determined in terms of its direction of motion, in the sense going up and coming down. Values of the attribute direction will define, of course, going up, coming down, and staying in one place. So these are the three states of an elevator: up, down, and staying at the same place. So we can define a simple finite state machine where we can, the transitions of states will essentially have this timing information. So it will be, let's say, going from S1 to S2. See, if the event is E1, so this is event slash action. So every transaction is annotated with an enabling event. In this case, the event is E1, and the action that takes place during the transition is that we set a timer, for instance, for 20 milliseconds. So basically, in an FSM, this is the terminology we'll use, which is event slash action. That on this event, you make a transition to state S2. And the action that you take is you set the timer, let's say for a certain duration, in this case, 20 milliseconds. So if I were to model the SS deadline constraint, which is that once a user completes dialing a digit, the next digit has to be dialed within the next 5 seconds. Otherwise, an idle tone is produced. The way that I would do is very simple. That the moment the first digit is dialed, I will. So this is the event. Okay, the event is dialing the first digit. This is the action. I set a timer for 5. So it's not milliseconds, 5 seconds. Then I await the second digit. All right. So if the second digit is pressed, then I again set the timer for 5 seconds and I await the next digit, the third digit. Otherwise, what I do is if I get a timer alarm, which means that the 5 seconds elapse and no digit is pressed, then I go to an I my the tone becomes an idle tone, and my current state becomes I await the caller to uh, on hook, basically replace the handset. All right. So the key idea is the event slash action. So basically, in the event, if a digit is pressed within the deadline, nothing much. I set one more timer and wait for the next digit. Otherwise, what I do is if I get the alarm, which means the time has passed, I just set the idle tone and go to the state where I want the user, the operator, to replace the handset, which means just put it down and again pick it up. So let's now look at the next RS type constraint. This is a response to stimulus deadline constraint. So the key idea is that once the dial tone appears, the first digit must be dialed within 30 seconds. Otherwise, the system enters an idle state and an idle tone is produced. So the RS deadline constraint is an example of a behavioral constraint. So the key point is that once the dial tone appears, I set a timer which waits for 30 seconds. And then I wait for the first digit. Okay. So if let's say that the first digit is dialed, so actually I should maybe have this like this. If the first digit is dialed, then what I can do is that I again set the timer once again. If there is, of course, there is a need. If there's a digit to digit thing, which is a more like a stimulus to stimulus thing. So let's say that since that has not been specified in the problem, I'm keeping that empty. But if the first digit is dialed, I go to a situation where I await the next digit. Or the alternative thing could have been what was written, which is if the dial tone continues, which means that I'm awaiting the next digit. Then, of course, I go down this track. But otherwise, if I have a timer alarm, in the sense if the 30 seconds are over, then my system beeps. So, which means it enters the idle state. In that state, it expects my receiver to replace the handset. Okay. The it expects the caller, the person who's making the call, to replace the handset. Now let us discuss a different kind of constraint. It's an SR deadline constraint where the R stands for response. So it is basically on the response. So it is more of a performance constraint, not a behavioral constraint. So the constraint is that if once the receiver is lifted from the handset, the dial tone must be produced by the system within 2 seconds. Right. So this is what you would expect. Right. That my job is that I lift the receiver of the phone. Within 2 seconds, I need the dial tone. Otherwise, a beeping sound is produced and the handset needs to be lifted. So, what is the event? The event is that the handset is lifted, and then I set a timer for 2 seconds. The state that I enter is I await the dial tone. I wait for the dial tone to be generated. If the dial tone is generated before the alarm, so of course, if you have multiple outgoing edges in this kind of an FSM, you basically take that transition, which happens the first, right? So, first, if we hear the dial tone, then of course we await the first digit. So, then we have entered a valid state. Otherwise, if the timer alarm happens in the sense that 2 seconds elapse, then there is a beeping sound, and then of course we enter the idling state, and then the receiver needs to be again put back, and you have to pretty much reset, right? Replace the receiver. That's what is called in traditional telephone terminology. An example of a response to response deadline constraint, again behavioral, that once the ringtone is given to the callee, so basically A is making a call to B, A is the caller and B is the callee. Once callee gets the ringtone, it starts ringing. The ring back tone, which is something we hear when we are calling somebody, that needs to be given to the caller within 2 seconds. Otherwise, the call stands terminated. So, what happens is the moment it starts ringing at the callee, we set a timer for 2 seconds and we await the ringback tone. The moment we get the ringback tone, again, the same logic holds of multiple outgoing edges out of a state. So the moment we hear the ringback tone, we enter a valid state which is awaiting for the first digit. However, if there is a timer alarm situation, then which means that 2 seconds elapse, we don't get the ringback tone, we terminate the call and we await for the receiver to again replace the handset. Let us model one more delay constraint. Once a digit is dialed, the next digit should be dialed at least after 1 second. Otherwise, same beeping sound and replace handset. No problem. Event is the first digit being dialed. Set the timer for 1 second. Await the next event. All right. So in this case, a delay constraint, mind you, will model it slightly differently, right? So we will not say that because in this case, unlike a deadline, this is a delay, right? So delay, you want something to happen after a duration. So in this case, we set the timer for 1 second, and the timer alarm going off in this case is actually a good thing. So what we do is if the timer alarm goes off, which means that 1 second happily passes, right, eventless, then basically we enter a valid state, which is the next digit, right? However, if let's say the first digit is, however, if let's say a digit is dialed, right? So if the first digit is dialed within that 1 second before the timer alarm happening, in this case, what we need to do is we need to terminate the call, right? So there is a need to terminate the call and replace the receiver because this 1 second discipline has not been followed. In the sense, two digits have been pressed in quick succession when they were not meant to be. So the example of a duration constraint, we've already seen that this idea of 15 seconds, 15 to 30 and 30 plus, right? So basically, to construct the model for this duration example, what we will typically do is that a duration constraint is then, so it's not modeled, so there is no way of kind of modeling the duration constraint independently. What we do is that we break it down or we convert it to equivalent delay and deadline constraints, and then those are shown in our FSM the same way that we were showing for others. The constraints will basically be for the start and end of it. So as I said, we need to convert them into equivalent delay and deadline events and model. So the model of the duration constraint in this case, if this was the model, this would look like this, that I'll press the button and I'll set a timer for 15 seconds. Then I'll await an event. If the button is released, then I go to the local operator. Otherwise, what I will do is that if there is a timer alarm, which means 15 seconds pass without the button being released, I set the alarm again for 15 seconds, which is like the period 15 to 30. Within this, if the button is released, again I contact the internal operator, right? And then, but if the button is not released, then the 30-second timer alarm goes off, which means that I'm here in the 30 plus range. In this case, again I await a button release. Once it is done, I have the dial tone. So what you see is that I have not modeled the duration constraint as simply as I was modeling the delay and duration constraints, but I kind of converted my, as simple as I was modeling delay and deadline constraints. What I've done is I've converted my duration constraint to delay and deadline constraints and modeled. So exercise one, two exercises. So those are things that the reader needs to do, which is if the temperature of a chemical reactor, let's say, rises above a certain threshold, T degrees C, the heater needs to be shut off within 10 milliseconds. Otherwise, the entire plant is shut off. Can you model this? The other is identify and model timing constraints, which is once the start switch of a washing machine is pressed, the stirring process commences, continues until a preset timer expires, or the stop button is pressed by the user. All right. So you need to model them exactly the way we have modeled the delay and deadlines in this lecture. So this lecture ends.